So today I'm going to talk about muscle action. Muscle action is about the gross activity of what's going on with muscles. Previously, we talked more about the molecular level with the sliding filament theory, about what's going on inside the muscle cell to cause contraction in the sarcomere. But let's see what the actions actually are for what's going on the gross anatomical level. There's two different ways you can think about exercise. One is isotonic and one is isometric. As you can see here in the definitions, it has to do really with generating tension. The tension is can be considered to be weight, but tension is actually the force that a muscle would be generating through the contraction. So if I lifted a 30-pound weight, I'd really have to be generating 30 pounds of tension. So let's talk about isotonic. That's the first one here. Now that's where joints move and the muscle length moves, but the weight, the tension is constant. And a really good example of that would be this picture over here. And you can see that person is lifting with free weights. So if I'm pumping up a 30-pound free weight, obviously my elbow joint is moving and my muscle length is changing, but the actual weight, the 30-pound weight, is not changing at all. Isotonic. Iso means the same. Tonic means tension in this case. Now the second type is this one right here. That's isometric. That's kind of the opposite. That's the one where the joints are not moving and the muscle length is not changing, but the tension you're generating by creating more contraction is changing. So a really good example would be crunches. So this guy over here is doing crunches, and if you've ever done that, you know it's kind of tough. He's lifting up his legs and holding in a position there and has to do a lot of tension to do that. His joints are not changing and the muscle length is not changing, but he's maintaining more and more tension to keep his legs up in the air like that.
Okay, so we're going to demonstrate for you the two types of exercises. The first type is isotonic. That's when the weight is constant, it doesn't change, but your muscles and your joints will change position. So here we go. This guy is a constant weight, although he's increasing in weight these days, but right now he's constant. And now, the weight is constant, but my muscles and joints are still moving. That's isotonic. Okay, Logan?
Okay.
Now we're going to demonstrate isometric. That's when the length doesn't change of your muscles and the joints don't move, but you can increase the tension by pushing harder and harder on the contraction of the muscles. Ready?
Yeah.
Head to head, arm to arm, go! You okay?
No.
Everyone understand? Good.
Okay, so now we're going to take a look at what's actually happening. Now what you're looking at right here, this picture way down here on the bottom, is actually a tension curve for a muscle. So let's imagine that we are changing the length of the muscle here. Now, we discovered last time that as more cross-bridging occurs between myosin and actin, you should get more tension. And that's what's happening over here on the y-axis. So when we find that perfect lengths where we get the maximum amount of overlapping, we get the maximum amount of tension. But as we try and push them closer and closer together, we start losing some of that. It gets too contracted, really, and you actually start getting less cross-bridging per unit and get less tension. Similarly, when you're way over here and they're farther apart, you actually get less tension. And that's actually why runners stretch their legs to begin with. They're trying to get them in that exact position where they're going to get the maximum amount of tension when contractions occur in the sarcomere. Let's look at the next slide here. Well, in this next slide here, basically you're seeing what's going on in the sarcomere. So, look at over here. Way down here, okay, you actually have the Z lines too close together. You have overlapping, but there's no more place where it can go. So you don't have a lot of tension. Similarly, when you're way over here, the Z lines are far apart. They barely overlap at all. As a matter of fact, I don't think these are overlapping at all. And so you can't really push them any closer together. There's no place for the cross bridges to occur. So only over here, when you find that sweet spot where you have overlapping to begin with, but there's still, if you see over here, plenty of room for them to increase their overlapping cross-bridging and create more tension. And that's what runners are doing when they stretch before they go out for the run. Okay, so we've talked so far about isotonic exercise and isometric. Let's talk about another variable, which is aerobic exercise versus anaerobic. Now, aerobic, people are probably familiar with. That's when you use oxygen, and anaerobic is when you don't use oxygen. We know that from bacteria. What type of exercises would use a lot of oxygen? Well, typically slow, continuous exercises use a lot of oxygen. So, Pilates, getting on the bike, getting on the treadmill, going for a long jog. Low, continuous, steady exercises tend to be aerobic, really build up the lungs. Anaerobic, conversely, is exactly the opposite. Those are fast bursts of exercise. So they degrade glycogen right away, but they don't really have time to incorporate oxygen in the whole pathway of cellular respiration. I hate to admit it, I'm a golfer, and so golf, unfortunately, is a good example of anaerobic. You get in the cart, you drink a beer, you get out there, you hit the ball, bang, a little burst of energy, and then you get back in the cart and drive to the next hole. So fast bursts of exercises would be a good example of anaerobic exercise.
Aerobic exercise is a slower, longer exercise like jogging. It will strengthen your heart and lungs. Anaerobic exercise like sprinting or weightlifting is a short, high-intensity workout. These exercises help build muscle and speed. Both are important parts of a complete training program.
For more information and to find more tips, go to our website or visit us on Facebook.
A third way to look at muscle action is the speed of the muscle. Now remember we talked about how myosin is one of the major proteins in the contraction of muscle. Well, myosin is also an enzyme. It's an ATPase. That's how we get the ATP to cross-bridge to actin. And it can do this fast, it can do it slow. So we have two different types of muscles, which are fast and slow contracting muscles. In general, fast muscles are dexterity and slow muscles are endurance. It's a really interesting example we can use is in chickens or ducks. You often, like a turkey, you talk about white meat and dark meat. Same thing when you go to KFC, order a bucket of chicken, dark meat, white meat. Well, what exactly is that? Well, it turns out that white meat is pretty much made of fast muscles, and dark meat is made of slow muscles. So, for example, if we were talking about a duck, the muscles used for the long endurance, the 4-hour flight, continuous flying action would probably be slow muscles, dark meat. And the reason why it's dark actually has to do with a type of hemoglobin called myoglobin, which those sort of muscles would have to have a lot of, and that's what gives it its dark color. Okay, moving on here to the next slide. Let's talk about muscle innervation itself. Very, very interesting. So the action potential comes down to the neuromuscular junction, and it jumps across through acetylcholine, and it causes an action potential. Every time a muscle fiber gets depolarized, we get a single event. So right here would be a single muscular event. That event is called a twitch. Let's go ahead and write that down here. That would be called a twitch. Let me give that a